All right, we left off talking about epoxides. I need to show you two things about epoxides, how to make them and how to break them. Epoxides are inherently reactive molecules. That's why they're used in epoxy resin. I don't know if we talked about this or not, but I'll bring up the epoxide reaction. But if that name epoxide sounds familiar, it is something you see at like hardware stores and at Walmart in the special section. It's a very, very strong glue. So it's something you'll commonly interact with. In order for an epoxide resin to work, you have to have the epoxide. So I showed you one way to make it, which is to take an alkene plus what? MCPBA, metachloroperoxybenzoic acid, turns an alkene into an epoxide. I won't rehash that here, but you know another way on how to prepare epoxides. That's supposed to be a cyclohexene. There you go. Anybody think of another way that you know how to make an epoxide that does not involve peroxy acid? It does involve a fictional bad guy from Captain America. Halohydrin, there we go. I was going to say every semester I make the stupid joke about how halohydrins sound like Hail Hydra, and it almost never sticks, but it stuck for two people. So that's my mental feedback to keep telling that dumb joke. A halohydrin comes from adding a halogen and water to an alkene. That is going to add across a double bond. Oops, not in blue. That's going to add across a double bond and give us a halogen on one side and an OH on the other side. And this type of molecule is called a halohydrin. Which internally I still shout. A halohydrin is formed when you add any halogen with water. So you could do this with a bromine on one side, a chlorine on one side, or an iodine, but most often you'll see chlorine and bromine used. And of the two, chlorine's used the most frequent. If you mix this in the presence of a base, and you don't even have to use a base, but a base can help catalyze this. So something like KOH, NOH, something that just helps remove that proton. You can get this oxygen to displace that chlorine. And if it does that, it would make this, which is of course an epoxide. You now know two ways in which to make an epoxide. Both of them start with an alkene. So if you want to make an epoxide, you have to start with an alkene. Now, why use one versus the other? They both have their downsides. I talked about how peroxy acids have this nasty habit of exploding spontaneously if they get too hot. How about this? Is that a super fun thing to react? Have you run any reactions in lab where someone's like, now open the bottle of chlorine gas? No, because that will kill you faster than the peroxide will. A peroxy acid will explode. You can get away from fire pretty well. You cannot get away from chlorine gas very well at all. It is very, very dangerous, right? So of the two, I'm going to use MCPBA because I do not want to work with chlorine gas. It's really messy to try and handle. Now that we've made our little reagents of death, what do we do with them? Epoxides only exist to open up. A couple things going on. One, three-membered ring. How do we feel about three-membered rings? Bat, boo, hiss. We don't like them because the ideal bond angles are hugely compressed. These carbons are sp3 hybridized. That means they want a 109.5 degree bond angle. They have a bond angle of 60 degrees. I'm not real good at math, but I'm pretty sure 60 is well shy of 109.5. Right? So the bond angle strain here is huge. The other thing that's going on is we have carbon-oxygen bonds. So not only are we compressing the bond angles from what they should be, we have a polarized bond in there that can break much more easily than, say, a carbon-carbon bond. So epoxides are very reactive. They are happy to open that ring. And that's good for us because we can use epoxides, we can bring in the chemical energy, the potential energy of an epoxide to run a reaction. And we're going to do this under both acid catalysis and base catalysis. And if you're in lab, if you're in the Tuesday lab, you know what a pain in the butt acid catalyzed reactions are. There are a lot of steps. The epoxide ring opening under acidic conditions is tough. There's more things to consider, there's more steps. The base catalyzed is easier. I'm going to show you both. All right, so the way this is going to work is we'll take our epoxide. We'll just use the one that we made up there. And we can open it up with something like H3O plus. So I know this is under acidic catalysis because hydronium is acid. So this is acid and water. And what we're going to get from this is a what? Transdiol. Fantastic. One of these OHs is going to be on a dash. And one of these OH, oops, let's do it the proper way here. Yeah, one of these OHs is going to be on a dash. And one of these OHs is going to be on a wedge. Now I'm putting them in different colors just to differentiate them, but you wouldn't know which OH is which. This is a transdiol. I think the transdiol of cyclohexane kills everybody on the planet, but the cis-diol cures COVID forever. Can we make the cis-diol instead? Moderately important life or death situation. This molecule, sweet, sweet death. Cis-diol, good. Nope, we're all just going to die. That's too bad. Osmium tetroxide is a way that we could put two OHs on the same side of that ring. So these are two reactions you've seen before about making OHs, a cis-diol on the same side or two OHs on the opposite side. Opening an epoxide gives you the OHs on the opposite side. I bet you're wondering how. I bet you know that I'm going to tell you. What's the first step of every acidic mechanism? Protonate something. Is there anything you can protonate in this molecule? Oxygen's got lone pairs, so let's give it one of these lone pairs. I'm going to drop the colors because it just gets to be problematic. The first step, oxygen's going to take a proton. Now what? Not a fair question. You've never seen this reaction before in your life. How could you possibly know what to do next? I took an already strained ring. Ooh, it's down low finally. I can point to it. I took an already strained ring and I made it even worse because I gave that oxygen a positive charge. So what do you think is going on with those bonds? Are the bonds holding the epoxide stronger or weaker? Weaker, meaning one of them really wants to break. What's a way I can break one of those bonds? And attack it with something else and pick it off. We could just consider this like a leaving group, right? And let's use the top one. We can consider that a leaving group. If something attacked it, it would be able to break that bond. And this molecule would love to break that bond. It would make it very stable. What's going to attack it? Water. There's two, there we go. Water is going to attack that carbon, break that bond. Lots of students want to draw this final molecule here. We're not ready to do that though. Water has two protons on it, which means there's an intermediate structure. And this is why acid catalyzed reactions are such a pain in the butt, because there's so many proton transfers that occur here. This oxygen that attached would be on a wedge because that's an SN2 reaction. It still has two hydrogens attached to it. That one's already an alcohol. How do I turn this into that? Water takes a proton. I love that you said water takes a proton. Why is it important that we show water taking that proton? There you go. This is acid catalyzed. So I start with hydronium. I'm going to finish this reaction with hydronium as well. If hydronium starts the reaction and finishes the reaction, then the hydronium is a catalyst. And really what we're talking about is the H+ is a catalyst. Water is an actual reagent. Water is consumed in this. The way you run one of these reactions is you take your epoxide, you put it in water. You could have like a big vat of epoxide in water. You put 1 drop of acid in and the reaction just runs and runs and runs and runs. You don't need to add very much acid. You don't need, say, I don't know, like a whole jug of acetic acid. You can have just a little, you could have like a little piece of acetic acid for it. Are there any questions? This is an inside joke for like 2 people. Are there any questions about epoxide ring openings? Has anybody used epoxide? Hold on, I'll come back to that. I have a thing to talk about. Does this make sense? Adding a proton, take the epoxide, add a proton to it, we destabilize it, something's going to attack it. The nature of what attacks here can be different. I'm going to show you one where we're going to use HCl to do this. And then we're just cleaning up proton transfer. So if you look at the number of steps that involve proton transfers, they make up the majority of what's happening here. Proton transfer, proton transfer. There's actually only one nucleophilic attack in this. That's common of most acid catalyzed reactions. When we deal with acid catalyzed ring openings, we have to worry about where things are. The fancy word for that is regiochemistry. We're going to break this down into, just like we talked about with ethers cracking open, primary and secondary and tertiary, or really if tertiary carbons are present. Here's an epoxide. I am interested in just the carbons that are directly attached to the epoxide. The carbon on the right, primary, secondary, or tertiary? Primary. The carbon on the left, primary, secondary, or tertiary? Secondary. Remember in OChem 1 when we did this and you were like, this is stupid. I don't want to learn about primary, secondary carbons. It matters. You need to know where those primary and secondary carbons are because it's going to change the reactivity. If I react this molecule with HCl, it can make 2 different products. One of them is going to have the OH on the secondary carbon, which means the Cl would be on the primary carbon. And one of them would have the Cl, let's put that bond in green, would have the Cl on the secondary carbon and the OH on the primary carbon. If I tell you that this reaction is SN2-like, meaning what's going to happen first is the oxygen takes a proton, we got that oxonium ion, and then the chlorine walks up to this and says, who am I going to attack? If the reaction follows an SN2-like pathway, which one of these products is going to be major? Left or right? Right. Who thinks left? Who thinks right? I can't tell you the answer and then also have people vote. This one is the major product. That's not how you spell major. Why? Because the chlorine attacked the primary carbon here, not the secondary. SN2 reactions are sterically controlled. When the chlorine walks up to this ion, it sees an easy place to approach. And over here, there's a couple defenders. It's going to attack the easy, it's going to attack the weak side that's not very well defended. Insert Arkansas Razorback joke. Does everybody see that? I'm going to drive. Some of you are not inspiring an overall confidence in me right now. When the chlorine comes up to this molecule, it's going, all right, epoxide, weak bond, ready to go. Am I going to attack the carbon on the left or am I going to attack the carbon on the right? The carbon on the right has 2 tiny little protons hanging out in space. You can run right past those, hit that carbon, break it open. Easy. The carbon on the left has a methyl group, which means the chlorine has to negotiate around that carbon. You go, well, I want to attack the epoxide carbon, but there's stuff in the way. So it takes the easier approach and attacks from this side, the less substituted side. I don't need you to memorize that primary versus secondary leads to the halogen or the nucleophile at the less substituted side. You can work this out if you just go through the mechanism on here. To this day, that's still how I do it. If you were to say, oh, in an epoxide ring opening under acidic conditions, what is the regiochemistry? I'd say, give me a second. And I'd like draw it out and go like, here's the major product. I'm too dumb to just like memorize that abstract concept. But this I can get, right? I can see a chlorine attacking the easier side. With me? When it flips, when we get a tertiary carbon in there, we have to change places. I'll leave that there. Carbon on the right is still primary. Carbon on the left is tertiary. If I react this with HCl, it is not the same anymore. I can make two possible products. The OH can end up on the more substituted carbon with the chlorine on the less substituted carbon, or the chlorine can end up on the more substituted carbon with the OH on the less substituted carbon. This is now the major product. That is the minor product. This type of reaction follows an SN1-like pathway. Now, why am I saying SN1-like, SN2-like, and why am I putting quotes in there? Because the mechanism is complicated. You can think of this kind of like once this oxonium ion, your green's a pretty good guy, but he cannot draw a triangle. I don't know if he's a good guy. The oxygen has a positive charge on here. What we're saying is that this bond effectively starts to break before the chlorine ever comes in and is able to attack. So when the chlorine approaches this molecule, it's not trying to decide between sterics anymore. It's basically seeing a positive charge over here versus a neutral carbon over here. If that bond starts to break early, then the chlorine is going to just be much more attractive to it. So this reaction is electronically controlled. In the top reaction, it's sterics. Both carbons are neutral. Which one can the chlorine get to more easily? It's going to attack that one. In the bottom one of those carbons has a real partial positive charge to it. You can think of it as like break the bond, then it attacks. That's not really what happens, but it's close enough. So sterically controlled. Electronically controlled. Does that make sense? The major difference between these two is how much does that bond start to break? Up here, you are not going to make a primary or secondary carbocation. It's just not stable enough. Down here, you can start to break this bond and get a lot of positive charge down here. The carbon isn't going to like it, but it can handle it because it's tertiary. Should we try one? Is it because it's cloudy outside? Is it because it's spring break next week? Is it because I gave you an exam recently? What'd the bad man do? Let's try one real quick. And by try one, I mean try two. Try these. I want the major products. The major products. And that's kind of misleading, sorry. So what I really want is, I want the major product for each reaction. one product per reaction. You know, if you guys keep pacing back and forth in the hall, I'm gonna make you come in here and work problems. Any takers? Hey, Vika, this top one, what are we thinking? Just like talk me through what's in your mind, right? The carbon on the far right is going to be the OH. Is this carbon primary, secondary, or tertiary? It's primary. How about the carbon on the other side? Secondary. So is this reaction going to follow SN2 regiochemistry, or is it going to follow SN1 regiochemistry? SN2, I agree. So we're going to use sterics to decide where that chlorine is going to attack. Is the chlorine going to attack the less sterically hindered or the more sterically hindered carbon? The less. So when we draw this out, I'm going to put the chlorine on this one, right? Which means the OH is going to go over there. Anybody want to try the bottom one? Yeah. Fantastic. So we over here, I think it's a good idea to just label the carbons in advance. You said the tertiary carbon, which one of those? Is it the left or the right? The right carbon is tertiary. Does everybody see how I'm getting to tertiary there? This can be confusing because there's 4 bonds coming off that carbon. So why is it not quaternary? Because it's only bonds to carbon. So this carbon has 1, 2, 3 carbons attached to it. That's why it's a tertiary carbon. That one's tertiary, that one's secondary, and Connor correctly identified this is going to follow SN1 chemistry, which means when we draw this out, we're going to have the chlorine over here and the OH over there. So what are you guys going to do when I give you an epoxide ring opening question on the quiz on Friday? You're going to slow down and take your time. The question's probably going to include something on there like watch out for regiochemistry. That's me telling you to slow down and be careful about who gets the OH and who gets the chlorine. It matters. Questions about opening epoxides under acidic conditions. Yeah. Cool. Yeah. Correct. If there's a secondary and a tertiary or a primary and a tertiary, it's going to go SN1. The reason for that is if you, this is going to turn into a weird metaphor, but here we go. It's going to be great. You walk up and you're a bank robber, right? There's one guard guarding like a little piggy bank. And then there's 3 guards guarding Fort Knox. If you're a bank robber, I'm going for Fort Knox. I don't care that there's 3 people in the way. The reward is much greater, right? The amount of money here is the charge. So as the chlorine's approaching this molecule, it doesn't matter that it's more crowded. It's so much more drawn because it has a negative charge. It's so much more drawn to this because of the positive charge that's developed there. Not only that, as that bond starts to break, that carbon gets flat because it's sp2 hybridized, which means it's easy to attack something flat from one side or the other. So having a tertiary carbon wins over anything else. Benzylic carbons are also, so if this was a benzene, I won't do that to you. But it's a good point. If that's a benzylic carbon or an allylic carbon, it favors SN1 regiochemistry because as that forms a positive charge, the benzene can help out. So it's a good point. I would expect fair amounts of both, probably. All right, so if you see acid catalyzed ring openings, yeah. If they're both secondary, you should expect, as long as there's no electronic differences between them, you should expect 50-50 products. That's for acid catalyzed ring openings. They are complicated. So you hope for base catalyzed ring openings, because guess what? They always follow SN2. If you have an epoxy, why I can't draw cyclohexanes today. If you have an epoxide, I don't care that one of those carbons happens to be tertiary. This is an exceptionally unstable molecule, by the way, but just for giggles, I can tell you're all in a giggly mood. That molecule has a tertiary carbon. There is a primary over here and a tertiary over here. It doesn't matter when I'm using hydroxide. So that's the tell that it's base catalyzed. There's no positive charge. There's no hydronium here. That'll be in the presence of H2O, but it's hydroxide. You typically want to heat these up. You don't have to, but it'll speed it up for you. Again, the reason you don't need heat is this system is already really high energetically, really unstable, high energy. That OH is going to attack this carbon. It is always going to follow SN2 regiochemistry. That's not the final product. The final product is going to be a diol. How do I get that to be a diol? It needs water. It needs to take a proton from water, right? There's water present in the system. If it takes a proton from water, that's really handy because what comes off? OH minus. Didn't we start this reaction with OH minus? And we finished it with OH minus? It's just beautiful. The circle of life is complete. OH is a catalyst. All sorts of nucleophiles can open epoxide rings. You've seen many of them. Alkoxides, amines, Grignard reagents, to name a few. Hydrides can do this as well. I'm going to show you a couple of them, but they're really important reactions because you can put an epoxide into a molecule and that gives you a handle for reactivity that you can then later run. So for example, I could have an epoxide. This epoxide, I don't know why that methyl group needs to be so flared. Go. And I could react it with ethoxide. We typically run that in its solvent ethanol. Ethoxide is going to attack the carbon on the left or the carbon on the right. This O minus is going to attack what? Carbon on the right, the less substituted carbon, because this reaction is SN2 controlled. When it attacks that carbon, that bond is going to break. We're going to form an O minus over here. We're going to have an oxygen over there, and then we'll finish that up typically in a second step. This would be step 1. Step 2, we have to add an acid in here. Although Yeah, I would add acid in here. The ethanol could also provide a proton if you wanted to. So this is not a must. No, I hate when you guys do this. Let me not do it. I don't hate when you do it. I encourage you to show me all the atoms in here. I love when you guys participate in this class in any way at all. That's what I said the first time. So show it taking a proton, show the electrons breaking on the hydronium. Give us our final product. You see one more? Yes, you do, because I'm going to bug you about these on Friday. What this? Grignard reagent, what do? Makes carbon-carbon bonds, right? It loves to attack things that have leaving groups. Typically, carbons have leaving groups on it, right? So this is an alkoxide on top. This is a Grignard reagent. I can react my Grignard reagent with a series of molecules. So let's see how we're doing. Let's just use an epoxide all on its own. We'll work it up with H3O plus. Get ahead of me. What is this going to make? And I can ask you what this is going to make because you can easily name the product. Hold that thought. What is it? No, say it. You're right. A primary alcohol. How many carbons is that primary alcohol going to have? How many? 6. Agreed. There are 1, 2, 3, 4 carbons over here. There's 2 carbons over there. The Grignard is going to attack one, break open that bond. So the OH, I like to think of epoxides kind of opening up like gates. It attacks on one side and the OH just swings open the other way, or attacks on this side and swings open the other way. That's what's going to happen. So we have our 1, 2, 3, 4 carbons with 1, 2 more attached to it, and an OH over here, which makes what, Peyton? Which one? I don't know if you guys noticed this or not, but I snuck it in there. It's a new carbon-carbon bond. We get real excited about those. Questions about epoxide ring opening? Now I want to bring up my example so I can jabber on while you're finishing writing down all this trash I just put on the board. Has anybody ever used an epoxide glue or ever seen these before, right? So a couple of you who are maybe into building or repairing things are familiar with these like syringes that you get. So if you go to Walmart, go over to like the specialty glue aisle where like Gorilla Glue and stuff is, you'll see these really clinical looking things where it's like two syringes that are attached together with a double plunger on top. What you do is you uncap it, you squeeze out the 2 materials, you mix them up, and you have somewhere between 30 seconds, if it's hardcore, and 10 minutes to do the thing before it hardens. And if you've ever messed with epoxide, you know, don't get it on you because you're going to lose some skin. You can literally cut airplane wings off of an airplane and glue them back on with epoxide and then fly the airplane through the sky. And the reason I know you can do that is because we do this. There is huge industrial applications for epoxide resins. They are very, very, very strong. They're very good at binding things together. And what they are in one of those tubes is an epoxide, the thing that's going to get attacked. And in the other tube, so it's a polymer of an epoxide, and the other tube is a nucleophile that can attack the epoxide. When you mix them together, you're forcing the nucleophile of one polymer to react with the electrophile of the other polymer. And when they form that bond, it sticks really, really well. Because we're going from such a high energy molecule to such a low energy molecule that the energy difference means those polymers are not coming back apart from each other. But based on the concentration, solvent, and nucleophile epoxide ratios, That's what sets your time limit. So you'll see on a bottle of epoxy, it'll say 30-second epoxy. Don't get 30-second epoxy unless you're really impatient. Because when it says 30 seconds, when you're done stirring, it's like you'll stir it and be like, done. It's game over. I want everybody to put their pens down because I want to show you one more application and I don't want to freak you out with it. It's very specific use of epoxides. This is an FYI with a little bit of a, you should know that amines do this as well. Here's a very specific molecule that an amine can attack. There's an epoxide. I can react this molecule with isopropylamine. We haven't talked about amines yet, but what do you think that looks like? An H2 with an isopropyl group coming off of it, right? So this is an amine. Here's the one part I want you to know. Amines can open epoxides. You don't need to know this epoxide. It's a big epoxide. But amines open epoxides in the same way that other molecules open epoxides. They can do it under basic conditions, which means my nitrogen is going to attack this carbon, the less substituted one, and break it open this way. A couple of other things are going to happen. Namely, I need to protonate the oxygen up here. And then I'm going to do another thing to kind of get rid of some groups down here. This thing's going to go away with conditions that you might be familiar with. So that's a reduction reaction. What I do is take this precursor molecule, first react it with isopropylamine. I pour acid and water in the flask. I clean all that up. Then I run that reaction through H2PDC. And at the end of this, it makes a molecule that looks like this. Let me draw it down here first, actually. So what the H2PDC was about was reducing this off through a mechanism you don't need to know about, but it blows off basically as acetic acid when it comes off of this. So it leaves me just down here. That's what the reduction's about. Up here, what's the top part of this molecule look like? Oxygen bond to here. Carbon-carbon bond there. Should probably put an OH here, right? That's from my epoxide opening up. What goes here? The nitrogen with the isopropyl group hanging off of it. There is now going to be one hydrogen hanging off of this. The name of this molecule is metoprolol. That sound familiar to anybody? For like a decade, this has been the #1 prescribed medication in the world. We make more metoprolol, a beta blocker, than anything else. It's responsible for blood pressure. And blood pressure affects like a couple people worldwide. What? Metformin is a related beta blocker. I don't think it's the same one. So if you work in a hospital setting, you've absolutely heard of this and you probably use this on the regular. An epoxide ring opening reaction makes this possible, right? So we do this chemistry a lot. So I know occasionally when we talk through this class, you kind of get like to a point where you're like, why the hell are we talking about any of this? It matters. You don't need to know how to make metoprolol, but hopefully you're a little impressed. Section 18.7 talks about crown ethers. I'm going to skip that. It's not that they're not super cool. It's that they're just really far out there. So there are molecules that I won't even draw them. They're ethers that are in rings. We call them crown ethers because if you draw them zigzag with the oxygens, they look like crowns. They're really neat for catching onto ions and things like that, but their time is kind of come and gone and they're kind of falling out of fashion. So if you're curious about crown ethers, give it a look. I'm not going to hold you accountable for it then, because I need to tell you about thiols and sulfides. Thiols are equivalent to alcohols. They are the sulfur equivalent. Sulfides are going to be the sulfur equivalent of ethers. So we're going to go through these pretty quick. The reason that they're in here is that you look on the periodic table, and I should put one on the board up here, but imagine the periodic table if you can't see one on the sides of the wall. Oxygen's right here. What's directly below it? Sulfur. Anything oxygen can do, sulfur can also do. Just the chemistry is a little bit squishy. So that's why we talk about them together. We even name them together. So if you have an oxygen with 2 carbons, the name of that molecule is ethanol. If I put 2 carbons, a sulfur on the end, we call that thiol, right? So the OL ending is meant to invoke a alcohol, but the thiol part is a sulfur alcohol. It doesn't fit very well because thiol starts with a consonant. So we're going to put the full name, ethane with an E on it, thiol. Leave the E. That's an uncomfortable thing. We're not used to doing that. The reason we leave the E on there is that we start with T for the next suffix. Every other suffix I showed you starts with a vowel. So we're replacing E with some other vowel and it flows nicely. Ethane thiol is how you refer to that molecule. What's the name of that molecule? What? There we go. I didn't draw no double bonds in there. How could you possibly get those confused? I'm kidding. They look really similar. Cyclohexane, leave the E, thiol. Thiols, as it turns out, are not that important. They are often referred to as substituents. Let's say I have something like benzoic acid. And I want to put a sulfur on there. So I'm going to name this molecule as a benzoic acid. And I want to refer to the SH group here as a substituent. We're going to use the prefix mercapto. And the thing that's super cool about that is the reason we call it mercapto is you might be familiar with mercury, super fun liquid metal that like doesn't stick to anything. And you're told to not play with it, but I'm saying this on a recording. Don't play with it. That's actually okay. The major issue is inhaling mercury or either inhaling it or swallowing it. You just play with it and wash your hands, you're fine. Because it doesn't stick to anything except for sulfur. It sticks really well to sulfur. So if you ever see a mercury spill kit and look inside there, you're going to see a yellow powder that smells really bad. It's an allotrope of sulfur. Sulfur is named mercapto because it's the one element on the periodic table that binds to mercury really well. So if you're wondering where that comes from, this molecule would be called meta-mercapto. It mercaptures mercury. Benzoic acid. Is that name mercapto familiar to any of you molecular biology types? Beta mercapto ethanol. Does that sound familiar to anybody? You need to take some advanced biology classes, what you need to do. That's an ethanol that has a sulfur on the other side of it. Questions on naming thiols? Okay, thiols can do, how far do I want to go? I'll do this last part. You guys have been good sports. By that, I mean, I'll do this last part and we'll get out like just a little bit early. Thiols can do this super cool thing where they can form thiol bonds. So sulfur-sulfur bonds are something that sulfur can do that oxygen's really terrible at. We call those disulfides. I can take 2 thiols and under oxidative stress, let me put this into the color here. If I oxidize them, I can make a sulfur-sulfur bond. And that is called a disulfide. Can I turn it into a different 2? All right, you asked for it. This is going to be 2 Two thiols come together to make a disulfide bond. Now, and when I say back in my day, loosely back in my day, I was born in 1985. So when teenagers in 1985 were doing their thing, they were all about that curly hair. And one of the ways you would get really curly hair would be to take your hair, put it into curlers, and then go see a nice lady or man, but most of the time a nice lady, who then sprays it with some really horrible stuff that forms disulfide bonds. What is that process called? A perm, a permanent curl. People don't do that anymore, and I think we should bring it back. What you're doing whenever you oxidize your hair like this is your hair contains lots of proteins in it, and some of them have cysteine. Cysteine has a thiol in it. You can get your hair to let those disulfide bonds go, typically with heat, right? So you can use a straightening iron. So if you have curly hair, you put heat and water across it, those disulfide bonds will let go, it'll lay flat. If you have curly hair and you straighten it and you spend all that time in the morning and then you go outside and it's humid, what happens? Pops right back. What's occurring is you've broken all the disulfide bonds with the straightener. The hair is laying nice and flat. Yet you go out into a warm, humid environment with oxygen around. Those bonds suddenly start to reform themselves really nicely in an oxidizing environment and start to recurl your hair. People used to, and I don't think we really do it much anymore, intentionally do this, where you would curl your hair, spray it with an oxidizing agent, all sorts of terrible stuff that you should not put on your head. And then when you take the curlers out, that curl stays in your hair for a very long time. The only way to break it is to apply heat and turn this back into free thiols. So the reverse reaction here is a straightener. And for those of you who regularly straighten your hair, you know the struggle of straighten, recurl, straighten again, recurl. It will just keep bouncing back. We will leave it there for now, and we will pick up with sulfides and NMR. Common. I'll see you all on Friday for the quiz.